everyone, thanks for watching. This is the second episode in my new Nerd Out series. Definitely one for those that like to get under the covers and look at some of the detail a bit. So if you're just looking at this for the first time or you've just found the channel, please subscribe. There's going to be more videos coming. Like the videos, set notifications on, share it, whatever you can do to help me grow the channel. I'd really appreciate it. So my goal is to get it up to 1,000 subscribers. I'd like to achieve that this year. I'm going to keep pushing the content out, so I appreciate all the help you can give me to get there. And please provide feedback to the video, put some comments in, any questions, things you'd like to see more of, just let me know. So my car is the Snotrocket. It's a Mark 6 Ford Fiesta that I use primarily on track days, and I've changed the engine throughout COVID and throughout lockdown. I've now got a Honda K24 engine in the engine bay. It's a tight squeeze, as you can see, and it's turbocharged, so it's a standard or a stock K24 A3 engine with the T4 turbocharger, and it's currently making around 340 horsepower at the crank. This video is to identify if there is a fuel pressure issue with the vehicle. When we mapped it on the dyno back in February, we did see some things that need to be looked at, and this video I'll try and keep it short and sweet and concise. We'll be talking about why we think there's an issue, what we think is causing the issue, and basically how we identified that. So this is a rough diagram that I found randomly on Google Images that shows kind of the architecture of the fuel system that I'm running. So I've got two fuel pumps. There's a low pressure pump that's actually within the fuel tank itself. That's down here on the diagram. I then have something called a swirl pot, which is like a surge tank, some people call it, especially the Americans. And what happens is the low pressure pump basically takes fuel from the tank, tops up the swirl pot, and then the overflow goes back to the tank. So the swirl pot is always full of fuel to the brim, and that kind of stops any issues with fuel starvation when you're on track with G-forces. And then there's a high pressure or high flow fuel pump that takes fuel from the swirl pot rather than the tank through a fuel filter as you wish, and then pumps that through to the fuel rail or the injector rail. A critical part of this discussion is the fuel pressure regulator. This diagram shows it being in line with the fuel rail doesn't go anywhere, but you can have the fuel pressure regulator before the fuel rail, within the middle of the fuel rail, like Honda do it from the factory, or you can have it coming out the back of the injector rail. It doesn't really make a difference. Fundamentally, the role of the fuel pressure regulator is to make sure that the pressure between the high pressure or the high flow pump is at a certain pressure that you want, a desirable pressure, between there and to where the injectors are. And that whole system up here around the edge is controlled, the pressure of it is controlled by the fuel pressure regulator. So this is roughly what I'm running on the car, or specifically what I'm running on the car. This unit here is the fuel pressure regulator. It's you may recognize it. It's the same type of regulator that an awful lot of production cars came with before engines went to direct injection. So this is on a port injection setup, which is relatively low pressure at 4 bar. That's a 4 bar fuel pressure regulator that's sitting in a housing that Webcon make. So you can run it external, and you can have different fittings. I'm running -6 AN fittings here that you can see. The arrows signify the direction of flow. So this hose here along the bottom, this arrow, this is from the high pressure fuel pump that goes up this pipe to the fuel rail with the injectors, and then the fuel rail returns back here down this pipe into the regulator. The regulator does its job, which is to regulate the fuel pressure to the injectors, and then this pipe here at the bottom of the regulator housing goes back to the swirl pot and ultimately to the tank. So it's a pretty basic system. You imagine the regulator is kind of like, you've got a long hose pipe. Along that hose pipe, you might have some holes on it, which are fundamentally the injectors, and then you've got your finger over the end of the hose at the other end. And depending on how much of the hose you block off, it affects the pressure that comes out the other holes along the path. Now, this is a crucial part of the fuel pressure regulator. So I'm not going to go into too much detail about absolute and relative pressure. Quick Google will help you understand that. But the fuel pressure regulator is a relative device. It needs a reference pressure to control the pressure that it supplies the injectors, or that it holds the injectors to. So this is a 4-bar fuel pressure regulator. The purpose of it is to make sure that the fuel pressure that comes out of the injectors is 4-bar relative to the pressure that the injector is in its environment. So if you imagine the fuel injectors are sitting in the inlet manifold, in between where the throttle body is and the inlet valve, the pressure inside those runners where the injector sits will vary depending on atmospheric conditions, or whether there's boost pressure being provided by a turbocharger or a supercharger, or if the throttle plate is closed, there could be, or there will be, a vacuum in there. And because that environmental pressure is changing, the fuel pressure regulator needs a way of adapting to make sure that the effective relative pressure that the injectors are running to is at the 4-bar that it's designed to do. And the way that that's configured here, you'll see this black hose here. This is a reference line or a vacuum hose. I mean, strictly it could have pressure in it as well, so probably not best to call it a vacuum hose, but a reference hose. That goes to the inlet manifold, which you can see on this photo on the right here. So this is tapped into, I think it was, I reused an existing fitting on here. It was probably to do with EGR or something, but either way, it's the sum of all 4 runners, the pressure within there where the injector is, and I've tapped into that to act as the reference that comes through here to the fuel pressure regulator. And here's a data sheet that just kind of shows you what's important. And if you focus on the areas highlighted in red, what this shows is at different fuel pressures. So let's look at the bar column, 3 bar up to 4, 5, 6, nearly 7 bar of pressure. The flow rate of the injector changes. So the more pressure, the more flow that you get from the injector. So it's important that, when you're running an injector on an engine, if you say, I want an injector that flows 1,000 cc's a minute, you want it to always flow 1,000 cc's a minute when that injector is open. Whether, if you've got lots of boost pressure or a vacuum or whatever, you always want it to flow the same amount of fuel, because that is important to getting your air to fuel ratio, your mixture, correct. So in my case, I'm running, say, 4-bar. These aren't the injectors I'm running, but it's all the same process and the same effect. So if we take, let's say 3-bar at the top, it's easy to understand. So at 3-bar fuel pressure, that injector will flow roughly 1,000 cc's a minute. Why that's important, I'll come on to in just a second. So you've got an injector, you want it to flow a certain amount of fuel, and to do that you need to keep the pressure static. So this is roughly, this is an architecture of an engine. This is a turbocharged engine, this diagram, and I know this is a little bit back to school, but fundamentally the turbocharger pushes air through an intercooler. That goes through, what's important here is the throttle plate, the throttle body. That goes through an inlet manifold and a plenum, and it goes into the inlet valve, into the engine. It gets burnt, it comes out the exhaust valve, and then goes back through the turbine on the turbocharger, and then back out the exhaust. So that's a very high-level diagram of how an engine works from an airflow perspective. This diagram is from a direct injection engine, which is not what I'm running. But if you imagine you've got the fuel injector here next to the spark plug, on my engine, that fuel injector would sit on the other side of the inlet valve here in the inlet manifold in the plenum. It doesn't make any difference for the purpose of this discussion. But what is important is whether you're running a turbocharged engine or a naturally aspirated engine, you are going to get a pressure differential, a difference in pressure either side of the throttle plate. And that's the purpose of it, right? So an engine is an air pump. That air pump will pull in air from the atmosphere, not turbocharged, from the atmosphere at atmospheric pressure. To get the peak performance of an engine is where the pressure going into the engine is the same as the pressure outside of the engine, so in the atmosphere. And in the case of a non-turbocharged engine, that's 1 atmosphere, which is roughly 14.5 pounds per square inch, or 100 kilopascals, which is a more meaningful figure. And if you want to reduce the airflow of the engine, so to slow the engine down to throttle it, guess what? You use a throttle body or a throttle plate, butterfly, And as you start to close that throttle, it restricts the amount of air that can go into the engine. So the engine's trying to draw it in as a pump, and the atmosphere is trying to push it into the engine through atmospheric pressure. As you close that throttle, the pump is still trying to draw air in. It can't. So what happens is, you, after the throttle body, between the throttle body and the engine itself, the inlet valve, you get a vacuum. And that's by design. So when an engine is idling and that throttle is practically closed, the engine's pulling quite a lot of vacuum. So to put that into perspective, if 100 kilopascals is atmospheric pressure, a normal kind of shopping car engine, not a full blown race engine, but a shopping car engine with reasonable cams, you're probably going to pull, or the pressure in the manifold after the throttle body is going to be in the region of 30 kilopascals, between 25 and 35 kilopascals. So you're basically pulling almost 2/3 or 3/4 of an atmosphere in vacuum just to keep that engine running at the lower speed. Because if you didn't have a throttle on an engine and you started it, it would just rev to the moon, because it's going to consume as much air as it can. And that's basically what happens when you open the throttle fully. It just consumes as much air as it possibly can to make the peak power that it's capable of doing. So that's the role of the throttle. And the fuel pressure regulator, on the previous photo, you saw that I had the reference line going to it. That would be plumbed in somewhere in here. So this area on the diagram is the plenum. That is the manifold pressure. That manifold pressure is where you take the reference feed for the fuel pressure regulator. The reason for that is, as you saw on the injector data, it flows, say at 3 bar pressure, it will flow 1,000 cc's a minute. Well, at vacuum, at idle, the vacuum in the plenum, like I say, you're taking nearly 3/4 of a bar, or 70 kilopascals of pressure out with the throttle, which means the 3 bar, the flow rate of the injector at 3 bar is going to be higher, because it's effectively 3.7 bar because of the vacuum. So where you've got 2 different pressures either side of a pipe, call that an injector or a hose pipe or whatever, where things will flow from a high pressure area to a low pressure area. And the bigger that pressure differential, the higher rate of flow there is. So if the pressure in the combustion chamber or the manifold is lower than the other side of the valve, you will get more flow than expected. So that 1,000 cc per minute injector at 3 bar, because what it's spraying into is at a lower relative pressure, it will flow more than 1,000 cc's, which is not expected. It's not what you want. So the purpose of the fuel pressure regulator is to adjust the fuel pressure to compensate for the environment that the fuel injector is operating in. And that works on a vacuum, and it also works on boost pressure. Most importantly, it works on boost pressure, because what you need is, as the turbocharger is pushing air into the engine, it's compressed, it's at a higher pressure. That's harder for the injector to spray fuel into. So if you didn't change the fuel pressure, if you didn't increase it in line with boost pressure, the amount of fuel that actually gets injected into the engine reduces. So your 1,000 cc's might become 700 cc's a minute, because you haven't increased the fuel pressure to compensate for the boost pressure that's within the engine. And that's super important. So, some people call them rising rate regulators or whatever, or 1-to-1 ratio. Fundamentally, generally you want a 1-to-1 ratio of fuel pressure to manifold pressure. So if the manifold pressure drops with the vacuum because of the throttle, or whether it increases above atmospheric pressure because of forced induction, you want the regulator needs to be able to adjust the fuel pressure to match that difference, so that you always get the same metered amount of fuel, whatever the condition. So when we were on the dyno, this was back in February, car set up on the hub dyno down at Torque Developments in Essex. It's my favourite dyno. It's a really good dyno cell, got good airflow, good cooling. But we wanted to do some extra tests. So here you can see the fuel rail. This silver component here is the fuel rail. You can see the fuel injectors going into the inlet manifold. But on the middle of the fuel rail, there's a takeoff where you can add a sensor to measure fuel pressure. I mean, you could possibly measure fuel temperature, but it's a bit tight for space to put a sensor like that in there. So We're taking off here a hose off of the fuel rail, and we're plumbing that into here. So we've got a remote sensor block that T7 Design make, so you can put multiple sensors in a common place and just run all of your hoses and sensors to it. And you'll see the other end of that fuel hose from here is presented into the bottom of the block. And then here we've got a 10 bar fluid pressure sensor that's plumbed into the ECU. So this will allow us on the dyno to see if we have any fuel pressure issues, if the fuel pump's doing a good enough job, because this was a brand new fuel system. We wanted to make sure that the low pressure pump that's in the tank was up to the job of flowing enough fuel. That's useful for tuning on the dyno, but it's also useful when you're on track and you're doing lots of high G-force driving, and you could end up with fuel starvation issues. So having a fuel pressure sensor is really important. When we originally mapped it, we were configuring the fuel pressure sensor, we were calibrating that in the ECU, and we started to notice an issue with it. And what I'll do is I'll flip over to the logs. I'll bring up a log file that shows us exactly what the issue is. So here we are. We've got a data log here. It's about 25 minutes long. This was from July by the looks of it. And this particular view, so just to recap, I'm using a Bowders Control Systems LPC AECU. Very capable, very good logging, very good analysis software for that particular ECU. And what we've got here is 4 charts specifically to support the fuel system to see what's going on there. What's important here is this second chart. So this second chart has got a few different channels in it, or sensors, and I'll just explain what they are. So MAP, manifold absolute pressure. So this is the pressure in the plenum. This is an absolute value. It's not boost pressure as such. If you want to see that as boost pressure, then you take 1,000 millibars away from it, and then that leaves you with the relative boost pressure in bar, or convert it however you want. The second value here is fuel pressure relative to barometric pressure. So barometric pressure is atmospheric, which is roughly 1,000 millibar. You'll probably see that on the weather. They'll tell you what the pressure is. Normally ranges between 990 and 1,010 millibar or something. And then the last value here is fuel pressure relative to MAP. Now, you know what I said about having the reference on the fuel pressure regulator? Purpose is that the injector is always giving out the correct metered amount of fuel, whatever the pressure is that it's the environment that it's operating in, at whatever pressure it is. So we'll cover off why this is particularly useful in a second, but what I want to show first is exactly what's going on with the fuel pressure and how it's not performing as it should. So I'm going to first of all go back to part of this log that is around idle. So if you look here, the top graph is engine speed. You can see there's some long flat sections here, which are idle areas. So if I zoom in here, so here's an area of idle. You can see at the top it's at roughly 800 RPM or nearly a minute. So it's just sitting there idling away. You'll see that the MAP value, before I said that, when you're idling an engine, the vacuum in the absolute pressure in the manifold is normally about between 25 and 35 kilopascals. Well, convert that to millibar. It's between 250 and 350 millibar, and this engine is bang in the middle. It's at 300 millibar. So that's basically 700 millibar away from atmospheric or barometric pressure, and that's how much of a vacuum it's pulling. So it's pulling 0.7 of a bar vacuum at idle, which is to be expected on an engine like this. Now, this is a 4-bar fuel pressure regulator that should be running. The pressure at the fuel pressure sensor should be 4,000 millibar less the vacuum that the engine is pulling, which is 700. So the value we should be seeing is around, under these conditions, is about 3,300 millibar. However, as you can see, we're seeing 3,800, which is not right. It's not pulling the fuel pressure down low enough that it should be based on the MAP value. So this is how you know there's an issue, and I'll cover off why I think that issue's there as we go through the video. Now, I said before that the fuel pressure regulator, not only does it reduce fuel pressure based on vacuum, but it increases fuel pressure based on boost. So if you end up with a positive pressure in the manifold, in the plenum, above atmospheric, above barometric pressure, then the fuel pressure should increase above the 4 bar or the 4000 millibar to compensate for that. So let's go and have a look through and see if there's an area of making some boost. So if we look at map, looking for a value over 1000, or let's just look for something where we've got some full throttle. There's a full throttle area here. So if we look down at this bottom chart, the accelerator pedal is in red. As you can see, this section here is full throttle. And what you can see is the map value increases, so that's the manifold pressure. It reaches its target pressure here, which is basically peak boost at 0.7 bar or 1.7 bar absolute. Like I say, you need to take 1 atmosphere away from that because it's absolute. And what you will see, the red line, which is fuel pressure relative to atmosphere, that increases at a similar trend to what the manifold pressure is doing, which is what you'd expect. So the fuel pressure regulator is increasing the fuel pressure to compensate for the boost pressure in the engine, and that gives you that consistent flow through the injectors that you need. Just to give you a comparison, where the white marker is, the values represent where the white marker is. So we're at 1.7 bar absolute pressure in the manifold, and the fuel pressure is at 4.7 bar. That's correct. So we've got 0.7 bar of boost above atmosphere. The manifold pressure is at 1.7 bar absolute, so that's 0.7 bar of boost. The fuel pressure is at 4.7 bar. Bearing in mind it's a 4 bar sensor, and because there's 0.7 bar in the manifold, the pressure regulator is increasing fuel pressure by 0.7 bar, which is correct and expected behaviour. So what we're seeing is under vacuum, can't pull the pressure down low enough, but under boost it's working quite happily. What that generally means is that the return from the regulator is not flowing well enough. So if you remember the picture, the photo of the fuel pressure regulator, there was a hose on the bottom of it that goes back to the tank. If that's too small, what can happen is at lower fuel flow rates, so when the engine's idling, for example, the regulator can't flow enough fuel back to the tank, and that stops it being able to drop pressure. So it needs to be able to work in a window of operation that allows it to flow, like bypass enough fuel back to the tank to bring the pressure down. So what happens is when you have a particularly high flowing fuel pump and a regulator or some pipe work that's not up to the job of basically bypassing that high pressure fuel pump, the pressure can never get low enough. So that's pretty typical. I think, when we look at this, it works fine under boost, so we think the regulator's working okay. It's just when you're trying to reduce pressure under vacuum, it's struggling. And a way that we can validate that, there's another value, I pointed this out before, there's fuel pressure relative to MAP. So this is a calculated value of what the fuel pressure is based on the manifold pressure and the actual fuel pressure that you've got. That should always be 4 bar. In an ideal world, the relative fuel pressure against manifold pressure should be the same pressure that the regulator is rated for. So I'll explain why that makes sense. So I said that the pressure is being hindered by the fact that if you don't flow a lot of fuel through the injectors, you're expecting the regulator to return the majority of the fuel from the high pressure pump back to the tank. And the theory is, which we'll prove one way or another in a second, the theory is that if you're flowing more fuel through the injectors into the engine, so you're making power, then that will help the fuel pressure regulator do its job, because it's not having to return as much fuel back to the tank because it's going through the engine itself. So we can see that here. This graph at the bottom, the third one here, the green line is the injector duty cycle. So that's the fuel injectors, it's the percentage that they are switched on per cycle of the engine. So when you fuel an engine, you basically map in how much the fuel injector opens per cycle, and that depends on how much airflow there is, how fast the engine's spinning, and other factors around volumetric efficiency. But that's fundamentally what happens. So as you can see, top graph, the engine speed's going up, goes up from say 2,500 RPM to 7,500 in this highlighted area. And what you'll see down here is in green is the duty cycle from the injectors goes up from 8 to 70. throughout that acceleration. Now, what's super important here is this yellow line. So this is where it should be showing 4 bar all of the time, because this is the expected pressure once the regulator has done its job. Now, we saw before that it could never bring the pressure down low enough. However, what you can see here is this yellow line. It starts to drop and then it plateaus. So from here to here, it's pretty flat. And when you look at the values here, the minimum was just under 4 bar, and the maximum, well, it's within, a fraction of each other. It's pretty much 4 bar once you get to this point. So if the theory is once the engine is consuming enough fuel that the regulator can do its job properly and there's not excess fuel to return back to the tank, then the pressure is actually working as it should. The regulator can establish the pressure that you want. So if you look at injector duty cycle, we get to about, I think it's about, let me just see, it's around 50% duty cycle, around here, that the fuel pressure reaches its relative 4 bar that it's designed to. So you can see that once the injector is flowing roughly half of its capacity or capability, however many litres per minute that is, that the regulator is not having to return back to the tank, then the regulator is now in its window of operation. It's not flat out at one end and unable to regulate the pressure. So that kind of shows, and I hope that makes sense, that shows that if there's a regulator that can't flow enough back to the tank, either due to the design of the regulator or the pipe work or some other factor, if you're asking that regulator needs to flow a certain amount of back to the tank to regulate the pressure and it can't, then the pressure will never drop enough. And that's kind of proven here with the data. Once the engine is discarding fuel or consuming fuel rather than returning it to the tank, then the relative pressure that you see is sitting at 4 bar, which is correct. And what you can, to see that further, as soon as we drop the throttle here, so you can see this red line down here, this is dropping the throttle back to 0. So we're now coasting down. The engine speed is dropping down slowly as well. You'll see that the relative fuel pressure shoots back up again, because it's not correct. It can't, when you're running at that point. So if I go here, look, you can see again, look, we're at 230 millibar of absolute pressure in the manifold now, which is a big vacuum. You can see that, the red line, the fuel pressure is at 3.9 bar. It should be at more like 3.3. And because of that, the relative fuel pressure to the manifold pressure is not 4 bar, it's 4.7. So that 0.7 is roughly the amount of vacuum that we're seeing in the manifold, but the regulator can't cope with it because the injectors are just not flowing any fuel into the engine. You can see this green line here, the injector duty cycle. The injectors are turned off now because it's on the overrun. And the fuel system, the regulator is just not coping with. So I hope that kind of shows how the regulator should be working, and it shows some of the data that you can use to understand where that potential limitation is. And I'll switch back now to why I think this is happening specifically. Okay, so I showed you before that the photo of the fuel pressure regulator that's in the car. This is what they look like when they're out of the housing. And what happens is you can see the white area here. This is the fuel inlet into the regulator. So as it goes around the fuel rail and back to the regulator, goes in through these white sections. And then this hole here on the bottom is the return. It's the outlet of the regulator. And that's the return that goes back to the tank. It goes out the bottom of the housing. It flows back to the tank. And you can see that's a really small hole, right? I mean, that hole's probably 2 millimeters diameter. Everybody worries about, do I need a -6 or a -8 hose back to the tank? It's like, well, look at the regulator first. What's the point in having a massive 10 millimeter hose when the actual outlet on the regulator itself is only 2 millimeters? Don't get me wrong, I'm not suggesting you only run the 2 millimeter hose, because there are other factors of friction and stuff that will cause issues, but you don't need ginormous hoses is kind of the point. So I'm working on the theory that this hole is too small. When the engine isn't consuming the fuel that the pump's pushing out, trying to circulate around the system, this small 2mm hole is frankly just not up to the job. So Webcon, I mean, the regulator on the left is a standard Bosch unit, used on Audis and other cars. And Webcon make this 4-bar unit on the right. It's a direct swap. It's a standard industry standard size and fitment. But as you can see, the hole in the return is considerably bigger relatively to the regulator that I'm running today. So I think what I'm going to do is I'm going to try one of these Webcon regulators, literally pull it out, do a direct swap, run the engine up, do some logging and see if that idle fuel pressure is now being brought back down to 3.3 bar where it should be, 0.7 bar of vacuum being pulled. And if it does, great, that's the problem solved. I could probably calculate how big that aperture's got to be based on, when we looked at duty cycle, roughly 50% of injector flow. Based on the flow of the injectors that I'm running, I could probably calculate how big that hole needs to be, but you're pretty limited. Unless I want to change to a completely different style of regulator, like a big aeromotive unit or something. If I want to use this type of capsule regulator, I don't think you're going to get one with a bigger hole than that. I'm assuming that diameter of that return hole in the regulator goes all the way back inside the regulator and it does actually flow more. But they're about £100, so you don't strictly need to do this, but if you want it to be controlling the fuel pressure properly, then it's worthwhile getting the mechanical elements of it right rather than expecting the ECU to adapt, which it does, but getting the mechanical stuff right first is important. So that's going to be the next step. Change the regulator to one with a bigger hole in the return, see if that solves the problem. If it doesn't, then I'll probably leave it as it is, because changing to a totally different type of regulator, whilst it may fix the issue, it's not really going to give any noticeable benefit to the operation of the engine, because it has closed loop fueling, it's very fast acting, it's got short and long term fuel trims in the LPCA ECU. It deals with it, right? It compensates for mechanical variations. But we've got the data, we're showing that the fuel pressure is not being controlled properly. Something in the back of my head that I'd like to solve, and this is going to be the next step. I hope that's been useful. If you like to see more of this kind of content, or if you want any clarification or have any questions, please get in the comments, leave your question, leave your points, tell me if it's good, if it's bad, and I'll carry on making more of this kind of podcast series as part of the Nerd Out series. So thanks a lot for your time. Look forward to the next one.